So I don't know that one of the graphics is going to work, but we'll give it a go anyway. I was asked to talk about sustainable transport and fuel cells. So I thought I'd kick off really by just giving a summary of where we see recent developments. So fuel cells really, I'd summarise as the last 10 years as being overdone really. They were overpromised. They were certainly overhyped. There's been a huge amount of hype, and they're definitely overdue in a transport context. They've consistently been presented as an imminent solution to a whole series of problems. And that problem, of course, has changed over time. Initially, what kicked this all off was the zero-emission vehicle mandate back in 1990 in California, and that was, of course, about urban pollution. That zero-emission mandate was written on the assumption that battery electric vehicles would meet the challenge, and that, of course, wasn't the case. So around the late 90s, the car industry really started investing a lot of money in fuel cell development for cars because of the battery inadequacies that were around at those times. And then today, things have shifted a bit. People don't talk about urban pollution as an issue for fuel cells anymore, but we talk about global warming. Of course, the urban pollution problem is still there. The technology has been 5 years away since I joined Johnson Matthey, which is 20 years ago, and it's still 5 years away. It's really a triumph of hope and aspiration, and actually the requirements of a lot of companies which need to go to the market for extra funding over the technical reality. As I say, Johnson Matthey's been involved in fuel cells for a long time. Since 1839, we supplied the platinum to William Grove when he made his first fuel cell. So we had a bit of an insight as to what's going on. And what I wanted to spend most of the first half of this talk just looking at is why I think things have really changed now. And we are moving into a new phase of a situation where the technology is getting ready. It's approaching what will be required. So here we go, this is the moment of truth. Oh, brilliant, it works. So this is just to put things in context. This is just a little animation of the fuel cells, how it works. And I'm just using this to be able to tie back some of the comments on later slides. So this, of course, the fuel cell stack is a series of cells, and these cells are typical membrane electrode assemblies. And the membrane electrode assembly is made up of an anode and a cathode and a sandwich in between that of a proton conducting membrane. What happens? There are within the stack itself there are of course no moving parts, and what we have is fuel, in this case hydrogen, which arrives delivered to one side of the membrane electrode assembly and is broken down, dissociated into hydrogen atoms by a catalytic layer on the anode. The protons, which then dissociate from the electrons of the hydrogen atoms, go different routes. The protons travel through the membrane, which is proton conducting but not electron conducting, so it's electrically insulating. And yet the anode, which is electrically conducting, can take the electrons and feed an external circuit. So all terribly simple. When the protons reach the other side of the membrane, they recombine again catalytically with oxygen atoms, which have been supplied on the other side of the cell. So it's all done by chemistry. It's all done by catalysis, and the catalytic layer, these very thin layers coating the anode and cathode, are the critical part where all of the action happens. And this is very important to be able to understand the later comments and the reasons behind some of the technology issues. So that's the schematic. The membrane electrode assembly in real life looks more like that. It's black products with a very thin piece of cling film in between, and that's the NEA. I mentioned before the catalyst layer is a critical bit, and this is a TEM of transmission electron micrograph, sorry, of a fuel cell catalyst. And the little black blobs you see are platinum active sites on a very, very highly dispersed high surface area carbon, which has got pores in it, and the pores are jolly important. They're jolly important because this is now taking that little catalyst layer and blowing it up. And the black thing you see in there is one of those pores. This is a transmission electron micrograph using cryogenic techniques, which allows, for the first time actually, you to us to visualise the proton conducting goo, which is the stuff that connects with the membrane to allow the protons to move. So we have a conducting substance, which is the carbon, which is the silvery stuff. We have a proton conductor, which is the stuff which will take the protons away. And we have a catalytic site. These are the platinum, currently platinum sites on the surface of the carbon support. And as I said before, the pore structure is very important because all of the action happens on the platinum site. You need, therefore, to have the platinum in intimate contact both with the conducting carbon, the proton conducting electrically insulating ionomer, the fluoropolymer, and at the same time allow quite a lot of gas in and quite a lot of exhaust gas out. So it's actually a very, very the background of what happens within the catalyst layer, and that really just sets the scene for the summary as to what I think we are in terms of technology. And before I go into this, what the little model that we use is to look at fuel cell development as a sort of hierarchy of priorities. It's not to say that you complete step one before starting step two, but we're saying that at any one point in time, you're focusing on the lowest incomplete level. So initially, of course, and this is for any product. Initially, does the product work? What's its in the case of fuel cells? That's really about power density. That's really about the ability of the fuel cell to convert to the sorts of currents which are required for automotive use. And that's actually quite high in automotive. We're operating at several amps per square centimetre of MEA. So that's really quite a heavy current density, and therefore quite a lot of gas to get in and quite a lot of exhaust to get out. Once we've got performance, we need to look at durability. How long does it last? What's its design life? Having looked at durability, how long does it break? What's the reliability of this product? And then finally, and this is the key point, finally, and only once you've got all of those, does it really start to matter to look at the cost of that unit. So where are we? Well, performance has pretty much been leaked in the 90s, and Ballard should take credit for an awful lot of work on that. And the power density targets that even automotive requires are now routinely achieved. And they have been for several years. Durability, and it was great to get the lead by John earlier, so he talks about durability. Here's some durability data. The durability requirements for an automotive fuel cell are in the region of 5,000 hours. That's the US DOE target. And we've been really showing a lot of progress over the last 5 years when it started to get important. In 2003, when we were really first looking at this seriously, durability was only in the region of 500 hours for in automotive conditions. And I stress these are under automotive conditions, which are the most difficult conditions for a fuel cell. And that was because the membrane tore. So that very fine membrane just couldn't cope with the stresses, the physical stresses that were placed upon it. That was fixed. Was fixed by another company than us, and introduced a reinforced membrane. And that took us up to a new failure mode. And the failure mode was this time that this inert fluoropolymer, which is used in the chloralkali industry, of course, dissolves. It's chemically attacked under the extreme and corrosive conditions inside a fuel cell. So we were getting failure after about 1,200 hours. That was then fixed by re-engineering the membrane and various other things to give us a durability which is now routinely above 3,000 hours in automotive conditions, which is frankly within spitting distance of the 5,000 hour target. So the big issue and the big thing that's been holding back fuel cells in transport applications appears to be approaching solution. We're not there yet, but it's now, as I say, imaginable that we're going to get there very quickly. And of course, in parallel with that, as I said, these aren't discrete issues. In parallel, a lot of work's being done by system developers to improve reliability of fuel cell stacks, and looking at engineering solutions to the geometries, and also things like freeze start, of course, critical for usability. So we have a reliability that's licked. The thing which of course is missing from there is cost. Fuel cells are prohibitively expensive. It's somewhat contentious to suggest that that's because nobody's actually looked at them yet. In some of the early markets that we have for fuel cells, and not in automotive but in electronic markets, for example, the metal loadings have gone down by a factor of 10 in the last 3 years. And that will happen. That will naturally happen when people start looking at them. Moment car companies, frankly, aren't interested, or aren't focusing, I won't say they're interested, they aren't focusing on cost reduction. So, that's enough for fuel cell technology. Really, just to summarise that, there's been actually quite a lot of progress over the last few years, in spite of the sort of downturn and people getting fed up with the hype. There are now real commercial applications for fuel cells, and those are not generally in transport. There are some niche transport applications such as forklift trucks, scooters and such, but the principal early markets for these are in things like electronic handheld devices, battery chargers, and in backup power. And these are real commercial applications where no subsidies are required, no sort of fudge factors are required to justify the purchase, and the business is growing. Transport technical targets, as we've seen, are now within reach. Cost is still an issue, but as I've said, it's not yet the focus. There are, however, significant issues still to overcome, and some of those are technology related, and we've heard this morning, and I'm sure we're going to hear this afternoon some more on the issues relating to hydrogen infrastructure, and particularly on-board storage. So I won't say any more about those. Costs, clearly going to be an issue, and will need to be addressed, but again, we have confidence and we have some precedents that is a manageable issue. And really, and what I'm going to focus the rest of this talk on is we have other problems, and these are problems related to market deployment and acceptance of a new-to-world technology, and new-to-world in the context of automotive. So it's no longer can the technology deliver. I think we now have a great deal of confidence that it can. The question is, when can the technology deliver? And one way of looking at that is to look at what the OEMs are saying. And I'm not going to go through all of those, but simply to say there's a sort of general consensus, conspiracy, people may say by now, general consensus that we're moving into a fleet trial kind of mode between now and 2010. And with commercial availability of fuel cell cars sometime around 2015. So that's all right then. It's all going to be fine. We've been there before. There's an awful lot of statements like this. Press statements aren't delivered under oath. And I think there's an awful lot of competitive jostling for position going on, and lots of other reasons for that. I prefer to be a little bit more systematic than to listen to the press releases. And the thing that we've looked at is to say, well, what's a good proxy for introduction of new technology? Well, perhaps hybrid electric vehicles are. And again, I'm not going to go through the schematic here, but actually hybrids are often used as an either-or to fuel cells. Actually, we view them as a very important and very useful transition technology to fuel cell. Now, hybrids, of course, are all about the electric control systems and drivetrains in automotive environments. Exactly what you're going to need for a fuel cell car. And actually, once you've got a hybrid, which is of course a combination of an electrical control of the drive and a mechanical control drive, it's actually a simplification. It's actually a cost reduction to take out the mechanical drive system and leave yourself with a fuel cell system, which of course will be hybridized. So it will be a hybrid fuel cell vehicle. So that's perhaps a useful proxy for us to look at. So we did a bit of looking. We came across sort of polls of hybrid sales forecasts. These were forecasts which were made and published in the periods, I think, 2002 to 2005, looking out at the forecasts of hybrid car introduction. And of course, we know what the answers are up to 2005 now. And so the 2000 to 2005, this is looking at the US market only, is actual. And the dotted line is the infamous regression curve fitted around those other ones. The error band in there is about 40%, actually, so it's not bad. There was reasonable agreement even 10 years in. What this says, and bear in mind that 2000 was actually 3 years after the commercial launch of the Prius in Japan, what this says is that by sort of 2015, we'll get 10% penetration of hybrid electric cars in the US. So is that good enough? It sounds 10% is a pretty healthy number. The Prius has been an absolutely spectacular success for Toyota. Of course, what 10% penetration in new car sales means is that 10 to 15 years after the introduction of this technology, 90% of the cars which are being bought are still conventional technology. And it means 99% of the car park is still conventional technology. Fuel cell hybrid vehicles, if these forecasts are correct, will make up 1% of the car park in the US. So is that good enough? Well, if you listen to the rather terrifying presentation on climate change, probably not, actually. And it actually also, if we look at it with a slightly different, from a different angle, look at it from a policy perspective, what are the requirements that have been cited? First of all, climate change. This is out of the DFT recently published innovation strategy. They say that 23% of total UK emissions comes from transport, and applying all of the policies which are currently projected using the DTI Markle model, we get 4% reduction by 2020. Probably not the radical change which the climate models are suggesting. The strategies, therefore, from the DFT paper, are considering looking at consumer behaviour changes, all of the modal shift and the consumer awareness, selection, downsizing, all that sort of stuff, and new technologies. So consumer behaviour, and as we've seen, that takes quite a long time. The other thrust which is being achieved is the introduction of new technology. So actually, probably 15 years to get to 1% penetration of the car park probably isn't enough if we're going to achieve the policy of a 20% reduction by 2020. Stern is what everyone cites, of course, in here. Stern's analysis, and I've just picked out a couple of quotes from there. Stern says it's impossible to imagine the reductions which are being forecast as required by 2050 being achieved without decarbonising the transport sector. He also goes on to say that despite the incremental improvements that have been happening in the car industry, the radical change which will be required to decarbonise the transport sector may not be delivered by the markets. And I think the only issue I have with that is the may bit. Will not be delivered by the market. And this isn't because of the car industry, really. If we look at fuel economy, and again, this is in the US because the figures are available. The CAFE standard, so this is the fleet average fuel economy in the US over 30 years. The CAFE fuel economy regulations forced up fuel economy in the early 80s, and it then hasn't actually moved in 20 years, average fuel economy. You can see the same effect as in Europe. It's a bit more complicated because of the change in market share of diesel. But if you correct for diesel penetration, the same occurs in Europe. So what's happened? What have these car companies been doing? Actually, they've been doing a lot. And it's not the case that the technology has stood still or that efficiencies of cars haven't improved over that time. What has changed is the weight of these vehicles and the performance of them. So the consumers have selected and have elected to buy better cars and buy safer cars rather than taking the benefit of the improved efficiency of fuel economy. And car companies which operate in this mature business, in this intensely competitive business, have correctly done what they do best, which is identifying customer requirements and meeting them. So they've delivered their customer priorities. So it's actually not the car company's fault, it's consumers' fault, we can say. And actually it's not theirs either, really. It's a disconnect between society and society wants a better environment. We together want a better environment, but individually we don't want to change our quality of life to get there. So society is buying the environmental benefit, but society doesn't buy cars, individuals buy cars. So it needs the assistance of something else. And of course the something else is what we rely on to deliver societal benefits, and that is government. And I'm running out of time. So the vehicle industry is very highly capable of delivery. You ask it to do something, given enough time, it will do pretty much anything. It reacts very well to its commercial environment. And there's little doubt that over time, if you introduce CAFE standards, you could get an incremental improvement. Maybe another 30% in 30 years. 30% is how engine efficiency has improved over the last 30 years. So you can maybe get another 30% in 30 years. That's not decarbonising transport. That doesn't deliver what's required to handle the climate concerns. And actually may work against introducing a new technology. So Stern, and again I'm going to go through this quickly, Stern says it's all about costs and volumes. We can move the break-even up by moving that green line, by introducing a carbon price which makes more advantageous low-carbon solutions. We can also provide deployment support to cover this cost gap, these high prices, the infamous valley of death for introducing a new product. We have a slightly different view of this. We say that it's not simply a valley of death as a mountain of risk. And the mountain of risk is because moving from having a technical product, a technically performing product, to a commercial product costs an awful amount of money, the product development costs. Now that is a cost all the time that you're putting the money at risk, because you're not certain about anybody's going to buy this. This is, remember, a new-to-world product. There aren't any fuel cell cars. You can't measure the market for them. So it's about risk, and anything that can be done to mitigate that risk, to make more certain the future market, to decouple the technology risk, which is what the supply chain is very good at in the car industry, from the market risk, will anybody buy these things, is really important. And that turns something which is a cost into an investment for the supply chain. So we promote an extension to the Stern analysis. We say deployment support is there. Subsidies are expensive, and what we need is measures to improve, to introduce the innovation of new products. And it's all about mobilising investment. It's not about subsidies and costs. Investment actually isn't affected significantly by grants. If you have a 25% contribution to your development cost, then it means you're paying 75% of it yourself. You're not going to spend 75% of the money if it's not a good idea. If it's a good idea, you're going to spend 100% if you're going to get a return for it. So it's very useful, and like any other company, nobody's going to turn down the offer of development support. It's not actually fundamental to making that investment decision. What is fundamental is markets and therefore revenues, getting a return on that money. And this is where we have a forward commitment procurement idea, where we try and fix the market outcome with a conditional commitment, and this is important, a conditional commitment that the product can be developed and can deliver at the right price and performance. So in the case of a fuel cell car, then it would be a cost and performance and durability requirement. particularly important to look at this cost effectively by looking at lead markets, and perhaps automotive cars is not the best market to look at. And what we'd like to, what we're doing a lot of work on is trying to identify a suitable lead market in the transport sector. And this is one way you can value the carbon advantage, where the technology is scalable, it can be used as a proxy, as an introduction for automotive, and it's supportable as well. And we think urban bosses fits that bill. They're often bought by municipal authorities, where there's a direct link, therefore, to the societal government approach, and significant procurement is possible. And that can then be built into delivery vehicles and public service. Key thing here is it's a commitment at some point in the future, 5 years in the future, to allow the supply chain to step up its investment in order to deliver a product in the future, and a product which doesn't exist today. So that's critical. Really, this is my final, just to summarise, I said we've got some precedents for it. It's all very depressing, some of this. This is a graph of this is emission control. This is another Johnson & business. And this is a graph of the controlled pollutants. The blue triangle represents what an uncontrolled car pollutant, car emissions are. So we have non-methane, hydrocarbon, NOx, and carbon monoxide. In 1975, oops, oh God. In 1975, we had a break. Try this again. Oh well, what you were going to see is how that triangle gets smaller and smaller and smaller. Actually, a factor of something between 1,000 and 10,000 from the uncontrolled emissions. And that was over a period of 30 years, between 1975 and 2 years ago. So 1975, the red was the first Clean Air Act requirements, and it ratchets up over time. Important thing is more time, more investment. By the time we get to, I'm going to try and stop it again, which might be a mistake. By the time we get to 1996, when I was actually in this division, and we're talking about SULEV, and SULEV is the yellow triangle you'll see coming up. It was impossible. It was absolutely impossible. The emission control industry, like the car industry, was quietly saying, God, how on earth are we going to achieve this? The SULEV requirements are now regularly exceeded, and the technology, given time, can deliver what is perceived to be impossible, and by the way, in the case of emission control, was impossible 10 years before. So I think we can have confidence that technology can deliver, and I think we're now in a different realm from where we have been over the last 10 or even 20 years in fuel cells for transport. So